Season 2, Episode 6, Experimental Extraterrestrial Exo-Observatory. And welcome back to another episode of the Syzygy podcast, episode number 6 in a series of 6 in this series 2 official of the Syzygy podcast. I'm sitting at the table in the office of one Dr. Emily Brunsden, and it's been a while, Emily.
I know, too long as usual.
Welcome back.
Yeah.
How long have you been back and where have you been? Just remind us and our listeners.
And I went Antipodean once again.
You've been back for 2 weeks. You weren't away for 2 weeks. You were away for longer than that.
Away for 2 months,
Yeah. Down in Kiwiland.
Yes, in New Zealand. Yep. Picking up some nice warm Christmas vibes.
Excellent. You missed all the grey on this side of the planet and got some good sunshine down there.
Wonderful.
Yeah. Around sort of the Christchurch area. That's
well, I was in the North Island for most of the time, but yeah, did visit Christchurch.
Yeah. What's summer like on the North Island of New Zealand? Is it sort of sunny and hot and
27 degrees, warm.
That's pretty good.
Sometimes humid, but mostly sunny.
That's not crazy hot.
No,
it's a good 20 degrees hotter than it was here. Very nice. Very nice. And a highlight of the trip, did you do any exploring? Did you what's the highlight of a visit to the Northern Island of New Zealand for someone in your position with a small person that you're dragging around?
Well, probably the little trip that I did for my birthday when I didn't have the small person, and we went to visit some very what we call backcountry New Zealand. Mm-hmm. So a bit off the tourist track, some nice little towns in the middle of the North Island of New Zealand, and it was Nice places, nice people, nice things.
Yeah. Well, welcome back. And you're back just in time for us to, slightly delayed. We had been intending, listener, to record an episode while Emily was away and then just somehow managed not to do that. I think Emily was just having too good a time and I was busy and we just never managed to get it together. So here we are. Yeah. But this is the final episode 6 in our series 2, which has all been about exo things.
Yes.
This entire series. So just as a quick recap, we started with exo moons.
Correct.
Curious place to start. You'd think we would go straight into exoplanets, but no, we decided to hold on to that. We did exo moons, we did exo comets, which I didn't even know was a thing. Turns out.
Yeah.
Then we did exoplanets. And then just to underscore it, we did exoplanets again, looking at JWST and sort of the present and future of the hunt for exoplanets and what we can learn. And we followed that up with what? What was episode 5?
Exotelescopes.
Exotelescopes, of course. Telescopes that aren't in the solar system anymore, which was a great discussion. I love just the mental image of these things winging their way out into the void, just beeping every once in a while. They're still going.
How many podcasts have episodes on exotelescopes,
I know.
do you think?
I think it's us and literally no one. I think we can pin that one on the wall. So for episode 6, what's left in the exo universe? Thinking about it, I guess most of the universe is exo-universe, isn't it? But, taking that aside, what's left in the universe of exo things for us to talk about? We've done all the things, right?
Well, there's kind of one glaringly obvious point we haven't touched on.
What's that?
Exo-life.
Ah, like ETs.
Yeah.
Extraterrestrials, ETs, exo-life. I mean, maybe not sort of little critters running around. I don't know that anyone is expecting the first detection of life necessarily to be from, little grey people wandering around with glowing fingertips, ET style. Although some people do, but I'm not sure how many scientists do.
Well, but no one expected the first exoplanets to be these hot Jupiters or indeed around pulsars.
There is that. So let's open our minds. Let's open our minds and today talk exo-life. Emily, have we found any yet? What's the latest?
No, is the short answer.
That's a shame.
Yeah.
Right. Join us for season 3 of No. We've got more to say on that.
Yes. No, okay, of course we do. So let's set up some parameters of the discussion today because you could go a lot of different ways with exo-life and you could talk about it for a lot of different episodes. But let's start with exo-life being the same definition as what we've used for the rest of the series as in beyond the solar system.
Okay, so we're not necessarily... I mean, it would be fascinating to find... be more than fascinating. Would be absolutely gobsmacking to find life like on Mars or on a moon going around Saturn or something. But we're talking exo.
Yep.
We're talking outside the solar system.
For the only reason is that was how we've defined the rest of the series. So let's just do that.
You've got to have rules. Rules are important.
Yeah. So I thought, where do you even start? And I guess since there's there's a body of research evidence about what we might do to start to look for life beyond the solar system. But there's also an important question of what do people think about looking for life beyond the solar system?
What sort of in a kind of meta sense of should we? Should we be doing this at all?
Maybe, but also just do you think it's worth doing?
Oh, I see.
Do you think that we're going to find anything?
Yeah, that's a lot of time and money and effort involved in doing something which, it's definitely worth asking the question. Could that effort and time and money be better spent?
Yeah. So I think it was. So I did look up a couple of surveys just to see what the general population thought about do aliens exist?
Right, because of course someone's done that.
Of course.
Someone's gone and asked.
There's many studies. Yeah. I mean, some of them are probably more reputable than others, and I'm not going to say necessarily that all my sources are the best ones, but they were the ones that I found.
But you have sources and you're prepared to share them with us today. So what have you found out?
So in the UK, we'll start with the UK, about 50% of people believe that aliens exist.
50%?
50%.
Wow, okay.
Yeah.
That's higher than, okay. Is that higher or lower than I would have expected? I don't know. Depends who I'm thinking about at the time. Okay, 50%.
Yep. About 22% believe they visited Earth.
Okay. Now we're getting down to brass tacks. Not only do they exist, but, they've been here. That's 1 in 5. Almost 1 in 4, Emily.
I know.
Wow.
Interesting, isn't it?
Yeah.
I did not, for maybe obvious reasons, look at the statistics for the United States of America.
Look, let's. I think we can probably safely say that the numbers would be higher.
Indeed.
Yeah.
And indeed, but I did look up those for Australia, and it turns out that 34% of Australians believe that there are aliens now on planet Earth.
34%. Not just that they exist, not just that they have visited, but that they're here now. 1 in 3. I think I've met a lot of those Australians. Yeah. Wow. We're a credulous bunch, aren't we?
So there you go. You
don't have the stats on New Zealand?
Well, I thought about looking them up.
Not a big enough sample size.
Well, I thought the numbers might actually not prove my slightly humorous point here, so I decided to leave that well alone.
Right. I was about to ask what your slightly humorous point was, but I think I know. Interesting. So, I mean, putting national sort of biases aside, that's quite high numbers. Quite high numbers. Given that, am I right in thinking we still have literally zero evidence of any of this? Like there's no actual credible, repeatable scientific evidence of there being life at all anywhere outside the Earth, let alone anything that's visited us, let alone anything that's here now.
Indeed.
Okay, good. So we've drawn that as a baseline. Yeah. We've got nothing, but loads of people think it's true anyway. Good. Welcome to 2025.
You can't grin like that.
Oh, dearie me. Right.
But let's put that aside for a minute, because that was just a little bit of an interlude, and say, well, okay, we don't have anything. How might we actually scientifically find something out?
Yeah. Okay. Let's put some scientific bones on this question. Let's shunt to the side any conjecture and just say, what could we do? Is this even a scientific question?
Well, it absolutely is. Is there life in other parts of the universe? Is there life outside the solar system? It's absolutely a scientific question.
Well, I guess what I mean is in the sense of like science depends on can you test it? So it's a perfectly good question. But if you haven't got a way to test for it, then there's not much science can say about it.
True.
But we can. What can we do?
Well, we think that we can maybe sort of kind of figure out a way that we might be able to test this.
Okay.
There's a lot of adjectives.
It's a lot of heavy lifting being done by some of those words.
Anyway, but okay, so what I wanted to actually talk about today was something that we've never talked about before, that I sort of only recently came into my sphere of understanding, and that is the very first telescope, because if you're going to find life on another planet outside our solar system, it's going to be done with a telescope. Yeah,
there's not really many other ways that's going to happen.
You don't have really any other options.
No.
So the first telescope from NASA, which is going to be its primary mission, is to search for extraterrestrial life.
Which is what?
It's called the Habitable Worlds Observatory.
Habitable World. I mean, I like the name. Tell me about this telescope. Where is it? What kind of telescope is it? Is it radio? Is it sort of, using visible wavelengths? What is it?
Okay, so
gravity?
We have to.
Not gravity.
No. So we have to imagine this is a telescope that's in concept, right? This is something we've not really gone into this kind of detail before, but you have many, many design phases before you get to the point of launching a space telescope. And this is indeed a space telescope.
Okay.
Space
all right.
telescope.
Yeah. For the obvious reason that, like, if you build it slightly wrong down here on Earth, you can just go in with a spanner. Like, it's harder than that. Obviously, these are very technical things, but you could literally pull it apart and fix it. You can't. In space, not nearly as easily. And also, like, it's got to fit in a rocket, and that rocket could explode. So,
well,
you want to be really, really, really careful, is my point.
Indeed. And so this is quite interesting because we're looking at something that happens in astronomy quite a lot is you set yourself an objective, a scientific objective. I want to understand about this. And you kind of work backwards from that objective. So you say, right, I want to know about, in this case, life beyond our solar system. What sort of telescope am I going to need? What information am I going to need to get from that telescope? What are the instruments I'm going to need? How much data is it going to, like, there's all sorts of bits you need to put together. And more often than not, when you start doing that process, because you're at the forefront of human knowledge necessarily, because you're asking the question.
That's the whole point.
You're already talking about something that we haven't got any design specs for. We don't understand how to do this. We're going to have to develop the technology to do it. We're going to have to develop the scientific understanding to figure out how to even answer the question.
Because by this point, if we did have the technology readily available on the shelf, and if we had done things like it before, we probably would have already addressed the question.
Indeed.
Like, someone would have done that. So the really interesting big questions are right there at that cutting edge of, can we even do this? Like, what do we need?
And it seems to be, at least from my point of view, things that I've seen, these areas of science that seem to do this a lot, at least, are astronomy. Particle physics actually does it quite a lot. Particle physics sort of says, let's just build a stonking great detector. And
let's just do it, but bigger. Let's bash them together harder next time.
But astronomy does it quite a lot. We're doing it with SKA, the Square Kilometre Array, which is saying, well, let's just build an enormous number of radio telescopes.
Yeah, what if you didn't have a big telescope? What if you had a really big telescope, but it was actually lots and lots of little telescopes spread like across the planet? What would that be like? And the answer is awesome and really hard.
Yeah. And, hey, we don't have the computer processing power to handle that data set.
No, but I'm sure we will one day.
But we might do by the time we actually get around to building it.
I mean, what's the stat that I remember from the first time I was reading about that? And we're going back like 10 years now when this was all first really being scoped out and I started reading about the SKA, was that the data that was going to be shunted around was the equivalent of like several times the entire internet again every day. So that's insane. Just from this one massive stonking telescope. That's nuts.
But that's not put anyone off.
No, we just need to do it, obviously.
Yeah. And there's other missions that are like that are currently in the pipeline, right? We talked about LISA, the interferometer that's going to look at gravitational waves. We don't really understand how that's going to work yet. And indeed, the Habitable Worlds Observatory is no different in the sense that we've got some broad ideas and we've got some really long lists, laundry lists, if you like, of this is where we have what we call technology gaps, meaning we don't really know how to build this yet. But we also, I think, really curiously in this case, have huge scientific gaps where we don't know how to understand the data yet, or we don't really know what data might answer the question yet.
That's really interesting.
Yeah.
Okay. So let's explore that today then. Can we back up a little bit before we do leap into that? In terms of sort of the history of looking for exo life, and the term that's been attached to that is SETI, right? The Search for Extraterrestrial Intelligence, SETI. And is it Jill Tarter? She's kind of one of the big luminaries of that field, Professor Jill Tarter. And that's been around for like decades now, right? So what are the ways that we have tried in the past to look for extraterrestrial life?
Yeah, so you are right. I'm being a bit unfair in the sense that I'm glossing over all the things that we do by just sitting here on Earth and waiting for signals to come to us.
Yeah, but I mean, I thought it might be worth just quickly, where, how have we got to where we are today? What have we done so far? The SETI community, I know, has used, big honkin' radio telescopes in order to try to look for anything from what would be, a very Hollywood style, oh my goodness, it's a sequence of prime numbers coming from this star, sort of the movie Contact style, through to, we've discussed on this podcast many times the fact that we can now start to see some of the characteristics of exoplanet atmospheres and so on, and looking for are there any signs of sort of the molecules that we would associate with life. So over a couple of decades, we've sort of gone from a very rudimentary, let's just look at stars and see if there are any interesting patterns. The most famous one, of course, was Jocelyn Bell Burnell and the pulsars, right? Which was initially like the first detection of a pulsar, which is a very, very regular oscillating radio signal, right? It's a spinning neutron star, am I right?
Yep.
And that was, at least tongue-in-cheek, called LGM-1. LGM standing for Little Green Men.
Yeah.
Because what else could possibly be sending such a incredibly precise repeating signal from space other than aliens? Well, turns out, actually, there
was
is
a star,
something.
but yeah.
So there's this sort of interesting history, but we've never really got to a point where we can definitively say, here's the way. Here's the way forward. And so that's what they're aiming for with this one.
Well, yes, but it is more specific than that. So if we took this question about is there life beyond the solar system, we can narrow that. We'll start to sort of draw some lines around that we can at least colour sort of between from that. So we are really talking about life in its broadest sense. We're not talking about just intelligent life, because one would imagine that, okay, on Earth there are a number of species you may class as intelligent, but that's certainly by no means the entire fauna, flora, population of the Earth, right? And
I'd hazard a guess that if you were looking from outside the solar system, there's probably only one species that you would have a chance of detecting amongst the intelligent ones. Like the dolphins aren't sending messages out into space at this
Not
point.
that we know of.
That we know of. I don't want to sell the dolphins down there. I'm just saying, we're probably it, right?
Yeah, exactly.
Yeah.
So, we wouldn't want to narrow our search to something intelligent or something that looks like, because that's being overly prescriptive for no apparent reason, really. Sure. So we are saying life in its broadest forms. So we're looking for, and we are also parameterizing this idea by saying, sure, you could possibly build life in different ways than how life has been built on Earth. There's a lot of science fiction to do with, instead of using carbon as your base element, you could use silicon because it behaves in a similar way.
Right, same column of the periodic table, it should connect to things in a similar way, so why not?
Well, yeah, but we just don't understand anything about how that might work. So
sure as hell no one's done that experiment, right? No one's built a kitten made out of silicon rather than carbon.
Not yet.
No. Again, that we know of, but I think
that's
fairly sure.
So to sort of put the scope into having the biggest chance of success, we're really talking about habitable planets, and we talk about habitable being similar to the Earth, because that's our data point of 1.
Sure, that's what we know.
And the one thing that we can observe on these other planets, apart from the ones in our solar system, is the atmosphere. So that kind of then takes you down to, if you're going to build something that's going to find life out there, you're going to want to identify these habitable planets, and you want to study their atmospheres for signs of life.
And I mean, that's all we've got, right? Like we can, it is staggering, absolutely staggering that we can see planets at all. Like I think we can all happily just live with the fact that we're really good at that now. Even more staggering is you can detect and start to sort of investigate those atmospheres. That's amazing. But just to be really clear, like that is the limit at this point. Like it's not like we can look through the atmospheres. and see what's down there,
No.
but we can infer some stuff from what we see in the atmosphere.
Yeah.
Cool. Okay.
So there's been a couple of missions that have been sort of working their way through the many, many, many stages of the NASA pipeline for a number of decades even. And two of them particularly got reasonably far through. The most famous one's called HabX, Habitable Exoplanets. And there was sort of a bit of a merger of those two concepts to get to the Habitable Worlds Observatory. So it's going to be NASA's next big thing after Roman.
Okay. Remind us what Roman is.
So Roman is the Nancy Grace Roman Space Telescope. It's an infrared telescope. I think they're hoping to launch around about mid-ish 2027. And of course, named after a really amazing woman who was she was a wonderful astronomer in her own right. She did a lot of work looking at the spectroscopy of stars and sort of looking at what chemical compositions of stars were, nearby stars to the sun, and sort of looking at what they were made of correlate with how they moved in the sky. And there was a lot of information that was able to be figured out about how the structure of the galaxy worked and things like that.
Nice. So that's supposed to be going up 2027. And just really quickly, like you said, it's infrared. What's its big mission goals going to be? It's similar to James Webb in a way, but it's sort of a bit of a broader mission. It's going to be looking more. So James Webb is quite targeted in its selections. Roman's a bit more wide field, looking towards the center of our galaxy, things like that. So yeah, it's sort of bridging the gap, I think, between what James Webb does, which is much more targeted, and what Kepler, the Space Telescope, did, which was very much just look at a point in the sky and see what happens. Right.
So it's kind of that mix. It's in between the two.
Somewhere in between. Yeah. And that's okay. So 2027, fingers crossed, everything going to plan. After that, then we're talking Habitable Worlds.
Yeah. So it's the next big thing.
And like, how far after? Like, how much in the future are we talking? Well, is this kind of a JWST where we'll launch it in 2028, 29, 2030, 33, look, sometime in the 2040s? We expect to get this off the ground. Sometime
in the 2040s is the current projection.
Okay, right. Yep.
Which is fine. And I think there are a lot of lessons learnt from JWST.
Don't make promises.
I've seen a lot of mention of budgetary controls. So that's fun affair. If you plan for that correctly and you understand where things could maybe go wrong budgetarily, maybe it won't be so bad.
But it also gives us a sense of like how hard this seems like it's going to be, because this isn't just, and we'll just wang it together after we get, the Roman telescope up in 27. We'll probably have it up by, the following Christmas. No, this is hard. This is hard to do. All right. So that's cool. Tell us about how hard that is.
So 2040s, we're looking at the basic design. There's a few sort of minutiae that's not really important, but the basic design is to put a 6 to 8 meter mirror on this telescope, which is pretty impressive, right? It's a big mirror. But the big thing that's going to be different to, say, James Webb, but will hopefully draw from Roman, is it's going to have some kind of coronagraph.
Which is what?
It's a thing that you put in the way to block out the light.
Oh yeah, it's the holding up your thumb in front of the thing so you can see the thing around the thing.
Which sounds like a silly thing. Why would you want to hold up something in front of the telescope that you're trying to get every single photon that you can?
Because we've talked about this, and I remember it's because the thing that you're blocking out is really, really bright, and you want to see the thing that's not so bright around that. So if you block out the bright thing, that allows you to pick up all the light that's not coming from the bright thing, that's coming from around the bright thing.
That's right. Yes.
So if you're looking in the direction of a star and there's an exoplanet that you're really interested in, then you block out the star and you get to see the planet.
Yeah.
Yay. I remember stuff.
Yeah, no, that's exactly right. So that's the basic kind of design. Now,
that is still incredible, right? Because stars are I don't know if you know this, stars are a really long way away.
I've noticed.
And so it's not like holding your thumb up, because it's like that would block out like lots of stars and all the planets and everything. That's got to be like, is it an actual thing that they're putting in the way?
It's a physical physical thing, yes.
It's going to be tiny.
Well, it depends on how far away you are from your pupil, if you like.
I guess so. Yeah.
Right? You say you're holding your thing at arm's length. You don't
Yeah.
have to hold your thumb at arm's length. You could hold your thumb up against your eyelid, and that blocks out quite a lot of stuff.
But that's my point, is
Yeah.
you don't want to block out too much.
No.
Like, having it further away means you can have it actually a bit small. Like, this needs to be really small just to block out the star, but not the planet.
Well, this is where it starts to become interesting. So we're missing a lot of stuff, the gaps, right? So we could start with the technology gaps.
Let's do it.
Because obviously the coronagraph is something that we've not got on a current space telescope. And indeed, there's still an open question about the coronagraph. Should it be fixed to the telescope, or should it float independently in space?
What? Seriously? Oh my goodness. I mean, this is like the Mars rover with the helicopter all over again. We're going to have a space telescope with a little buddy?
Yep, and we're probably going to give it a name, I
cool.
guess.
That's so cool. I hope they do that. That would be great.
So there's reasons why you might want it fixed, and there's reasons why you might want it free floating. Free floating is hard, but potentially beneficial because you've got a bit more control over what you're doing. But yeah.
On the other hand, I would have thought easier to lose. Has anyone seen the coronagraph recently? I thought you had it. No, it's just kind of floating off over there now. It's lost power. Yeah, that would be bad.
Well, so humorously, I guess, because the plan is to launch this telescope to put it at L2, which is Lagrangian point 2, our favourite place for many space telescopes.
Yeah. Is that? I can't remember. Is that where JWST is? Yeah.
Yep. As Kepler, as
getting crowded, aren't they?
Yeah. So you can almost think, well, the other space telescopes looking over jealously, saying, "Oh, you got a coronagraph." That's quite cool.
Coronagraph goes and starts hanging out with JWST.
Anyway,
everyone gets jealous.
We're a bit silly, but So that's it. But that is genuinely a design challenge and technology challenge.
So we don't know how to do that one yet.
Nope.
The idea is we're going to have a chronograph. Yeah, how are we going to do that? Don't know yet.
Yep.
We're working on that.
Yep.
We've got a couple of years.
Yeah.
Yep.
And it needs to block about 10 billion times the light. About 10 billion a factor of 10 billion of the light suppression.
So hang on. Explain that. As in, if you've got the brightness of the star, you need to reduce that by a factor of 10 billion by blocking out the star bit to see the bit around it.
Yep.
That's quite a big number.
It is a big number.
Yeah.
Anyway, working on it. The other technology, I mean, there's loads of technological challenges, and there's some really interesting well, I guess it depends on what you're into, but there's some really interesting, very in-depth literature on the analysis of the technology gaps. There's teams that are looking at where the gaps are, what the current state of the art is, and categorizing the technology gaps from kind of, no, we really need this, otherwise this thing won't fly, to this would be really, really cool to have, but maybe it's a bit
put that
ambitious.
One a little bit further down the list.
Yeah.
These are the definites, and they're the icing on the cake. Yeah.
Because you think, between now, with 2025, 2040, let's say it's going to launch in 2045. So you've got to have your technology wrapped up really probably by 2040 if you want to launch in 2025.
One would imagine, because you've then also got we now know how we want to build it. Now we've actually got to build it in a way which is going to get into space. And a lot can change, as I imagine they found on JWST. Well, indeed. Problems come up.
Indeed. So that's 15 years or so of R&D. That's a pretty hefty chunk of someone's career, just looking at how we might meet some of these challenges. So, it's pretty interesting. But some other challenges might be things like the telescope stability, because if you've got a little tiny coronagraph covering up a little tiny star, you want to be pointing your telescope very, very accurately, more accurately than current space telescopes point. So I think the goal is around about picometer precision and stability.
Now, picometers are very small meters. It goes millimeters, and then micrometers, and then nanometers. We're going down by a factor of 1,000 each time.
Yep.
Nanometers, and pico's another 1,000 down from nano.
12, minus 12.
So 10 to the minus 12 of a meter. That's a millionth of a meter. That's small. That's
So-
small. Hang on, 10 to the minus 12. That's smaller than an atom.
Yep.
Holy cow! that's 100 times smaller than an atom.
Yes.
Bigger than a nucleus, but not a lot.
No.
Holy cow!
Bigger than an electron.
That's
but, yeah.
insane.
Yes, so
Yeah.
really, really high precision. Because otherwise it just won't work. I mean, if your shield moves, it's the thermal stability that's actually really hard at that level because the sun's rays
do
will
you
be
even do
hitting
that?
you at
Like,
different angles.
What kind of are we talking about? Sort of, getting things down to ludicrously low temperatures. Like, are these?
Yeah, you
like
have to. Well, you have
super
to.
cooled
You
or
have to
something?
cool, and then you've got to maintain those temperatures very, very precisely.
That's nuts. And in space, like where you can't just get in with a spanner and fix the thing.
And as we've learnt with JWST, lots of micrometeors tearing about.
Oh yeah, that's not good. Yeah.
So you've got to be able to cope with the impacts. Of
Maybe they
those
need another
ones.
little buddy up there with a big umbrella holding it up.
Yeah, so that's quite interesting. Lots of obviously improvements needed in detector sensitivity. We're doing, you're pushing the limit, so you need to have improved detectors. And particularly in terms of the atmospheres, we need to have very high resolution spectroscopy to understand the chemical composition of the exoplanet atmospheres.
Yeah, I mean, just getting to the point where you could read it at all is hard, but then you've actually got to understand what you're looking at, which we'll get to in a minute, I guess, which is the science part. But being able to sort of tease apart at that incredibly, sensitive level.
Yeah.
What are we looking at?
So you need to be able to say not only is there, say, oxygen there, but how much.
Wow.
Yeah,
Yeah, okay, I can see why we're not throwing this up into space anytime soon.
indeed.
Yeah.
And the last little bit of technology I thought was quite interesting. And I wonder if this is just a little NASA quirk or if this is kind of something that they are seriously considering. I saw there was a sort of a pre-mission conference last summer, which was for university students, where they could go along to NASA and just find out about this observatory and some of these technical challenges. Because I guess today's university students will move on to be potentially becoming the engineers and scientists who are trying to address these problems.
Yeah,
right?
I mean, as you said, we're talking 20 years' time. Maybe it'll be launched. 15 years' time, it'll be prime development. People in school today will be doing that.
Well, actually, I did look this up. This is a rather scary one. Yeah. If you want to do your PhD on the first data coming off the Habitable Worlds Observatory, you're probably looking to be born at least 2015, probably more in the 2020s.
Well, I mean, you've got one of those in your household.
Yeah, that's a bit of a scary thought, isn't it?
Yeah. I mean, it's nice to know that there's something that Robin might get on with. That's good.
Anyway, so they were looking at some of these design challenges, and one of the things that the undergraduate students were looking at is, let's throw your ideas at us and design a robotic mission that might be able to service such a telescope and actually do, for example, an instrument swap, because you put your wonderful telescope out there. Often with these things, there's nothing wrong with the mirror, with the optics, with whatever, but you might, in the meantime, and this has happened with Hubble many, many times, you find ways to develop your instrumentation of what you can measure from that telescope, and you want to upgrade it and replace it.
Yeah, and Hubble is Hubble low Earth orbit? It's just up there.
Yeah.
Like you'd almost touch it. That's hard enough. But you could do it with like the space shuttle, right?
Well, we did for a number of years.
When we had them. But L2 is a bit different. That's much further away. You can't just sort of duck up there and swap out a bit.
No, and you wouldn't send people to do it. So this would
something
be
robotic, to kind of wing its way up there and swap out an instrument.
Because if you can send a space telescope to L2, why couldn't you send a little robot to upgrade it?
Just because we've never done it before.
Indeed.
Yeah, that's fun.
So I think part of the design will be a little bit of modularization of the instrumentation, with the idea that maybe we will be able to upgrade them in time, which is kind of cool.
Yeah, that's a really nice idea. Because that's not, as you say, that's not something that's been built into the specs for JWST.
No.
Like it was sent up there and like, look, you've got what you got, right? You're on your own now.
Yeah.
Yeah.
And things like liquid helium for cooling and things like that always run out for these telescopes. So, yeah, and gases just run out. So it'd be good to just top them up.
Yeah.
Carry on going.
Nice idea. So lots of technological issues to overcome, lots of challenges. Yeah. But then there's the scientific side.
Yeah. So this is where it gets a little bit fuzzy. So you might say you want to detect life on a exoplanet.
Sure, that's the point. That's why we're here.
So you would go for what we call a biosignature. So something that tells you that there is life, a signature of life, right? Biosignature. The problem is we don't really know of any good biosignatures.
But surely we're surrounded by them. Like, can't we just sort of look around us here and go, what do we got? What shows that we're here?
Absolutely, absolutely. I mean, you can say, well, there's lots of oxygen, for example, on Earth. There's water, there's methane, there's phosphine, whatever, right? These are things that, for example, on Earth are produced by life. The problem is that there are ways to abiotically, so based on just things that are not life.
Just chemistry.
Yeah, produce these things as well.
Right. So what you're looking for is not just around life there are these things, but unambiguously that thing means high probability of life.
Yeah.
Right.
So we don't have...
Turns out that's harder.
We do not have a single biosignature that is unequivocally only because of life and cannot be produced in any other way.
That's fascinating. If you'd asked me, I would have put money on, but surely out of all of the different ones, but there's this one or there's these half a dozen. Like there's no way you'd ever come across chemical species X, molecule Y. There's no way that you'd get that unless there was all of this, biological stuff going on. Turns out no.
So you can't just go and look for oxygen or look for water and say, hey, that planet is inhabited because of that.
Because there's lots of places that have oxygen and water.
Indeed.
Turns out.
So
are there any good candidates?
Well, not as a single species, really. I think we can put to bed the idea that you find a single species of something and that means life.
Right.
That's probably just not going to happen.
The smoking gun of life ain't going to be there.
Exactly.
Okay.
However, there's a lot of work going on into how you can look at what we call disequilibrium environments. So on Earth, we have a disequilibrium in our atmosphere because we are, carbon producing humans. Even take away the fact that the climate change caused by people, you've got just the fact that life on Earth causes a balance of the molecules in the atmosphere, which is unlikely to be produced by simple geological processes.
Right. So even taking away the fact that things are considerably out of balance right now, if you were to look at a whole range of different molecular species in the atmosphere, what are you saying? That you'd be able to sort of reverse engineer that into, look, it's pretty unlikely that's going to happen unless...
Yeah, well, you could take the example of methane. So methane, you've got to have a constant production to have a substantial amount of it in your atmosphere, because otherwise it just
it goes away.
Yeah.
It degrades or turns into other things.
Exactly.
Yeah.
So if you're seeing it and it's there, then it has to be continuously being produced. And so in the case of Earth, methane is produced by lots of different animals and people.
Right. And that doesn't mean that there aren't things that could produce methane that aren't alive, but it's just one example.
Yeah.
So the point then being, once again, you can't look at any individual molecule, but you can start to build up a bit of a picture by looking at enough molecules, enough species, enough things in the atmosphere, which presumably is why you need all this technological advancement in the first place. This is hard.
It is hard. And much like actually the individual species, there's still no perfect ratio of if you have this much methane, this much oxygen, this much nitrogen, whatever, then you've definitely got life.
Right.
There seems to always be some way that you could geologically basically produce a very similar environment.
I mean, that's fascinating, isn't it? It's almost like chemistry is trying to tell us something there. I don't know what it is, but it's not that simple. Life's kind of complicated. So how do you get around that? What's the science trying to do with that then?
Well, I think that's what the next 15 plus years are
Right.
really for, is to try and figure out what could be a really useful biosignature. And what is probably going to be some ratio of chemical elements that are going to, or molecules which are going to be the perfect biosignature.
And again, it's so tricky because we don't even know, like, we're making assumptions about the nature of the life. Because we've only got an N of 1. But you've got to leave that window open wide enough to be able to go, but maybe it's a little bit different up there. And so maybe it could be kind of like this. We don't know.
But we can start approaching the question from the other direction and say, well, if you have a planet, it has this sort of chemical makeup, because we know that, like, we understand most of what the Earth is made up of, and we understand most of what the other planets in our solar system are made up of, and we mostly understand how that relates to what the star is made of. So if you see another star in another system, you can start to figure out what those other planets might be like, and then you can start measuring the temperatures and seeing what that's like. And once you've got some atmosphere, you can start to put together, I guess, the puzzle pieces from the other direction and say, well, what should the planet's atmosphere kind of look like?
Right. Yeah. Building up a template for, we would expect planet here to be like this with no life. We see this, subtract one from the other. What do we got? And can we make any sense of that whatsoever? We're a really, really long way away from a sequence of primes being sent by radio waves, aren't we? This is hard.
It is very, very hard. But that's why I think it's so exciting as well, because we're basically saying, look, we don't really know what we're looking for. We kind of know how to do it, but there's a whole lot of things that are the details, important details, that we don't know how to do along the way. But let's just go for it anyway.
Let's see what we can see. And if that means that we have to make machines that can do things that we've never been able to do before in order to try to find this out, then surely that's a win-win, right?
Yeah, exactly. And this has been, I think, how we've thought about extraterrestrial science for a very, very long time. Even going back to the Nancy Roman, who the Roman Space Telescope is named after. She played a huge role in the development of Hubble. In fact, sort of adopted the nickname of the mother of Hubble.
Oh, right.
And you can see how and her career didn't necessarily benefit from Hubble itself, but obviously that built the careers of thousands of astronomers, astrophysicists, space engineers, etc. Right? And so I really like this forward thinking that you have in science of thinking, okay, this is the next question. We can put entire careers towards setting part of that up for the next generation of scientists.
Yeah. I mean, the extraordinary work that went into over a very long period of time in getting currently the most complex piece of machinery we've ever put into space being JWST. Like, it's really hard. And now that's simply, the baseline for whatever follows after that. We've learned a whole bunch of lessons from that. Kind of know how to do that one. If we were to do it again, might do it a bit differently, but let's move on and do something even harder. Or you were saying before, about there was the LIGO project with measuring gravity waves. You go back 100 years, the notion of measuring waves produced by enormously energetic things off across the other side of the bloody galaxy, making waves in space-time itself so small. We will never, ever be able to measure those. Yeah, give it enough time. 100 years, turns out we can. Really, really hard. But now that we know we can do that, let's make a better one, which we've done. It's, everything just leads to the next one.
Yeah.
This one sounds hard.
It is hard. But I would say, I think generally, if the international scientific climate makes you feel a little bit sad in 2025.
Can't imagine why, but let's hypothetically say.
Let's say that might be the case. I think take a step back and maybe think of the altruism of these projects. All of these projects, SKA, LISA, the Habitable Worlds Observatory. How many people are putting whole careers towards setting up the next 3, 4, 5 generations of scientists.
Yeah.
It's very exciting.
It does kind of put whatever relatively short-term impediments that might happen, kind of puts those in perspective. That scientific progress is long-term. Keep your eye on the prize, because you couldn't stop it if you wanted to at this point. So just keep going. Yeah, nice. I like that. That's a bit of bloody positivity for February 2025. I like it. We need that. Well, Emily, that brings us to the end, not just of this episode, but of this season of Syzygy. We took a punt with season 2. We said season 1, 115-ish episodes, the first 115. Let's put all of that into season 1. Season 2, let's talk about exo things. And the whole reason for doing that, listener, is so that we could focus on a particular topic and then take a bit of a break and recoup and come up with a plan for the next one and focus on that, rather than what we've tended to do, because life gets busy, of dropping in and out and waiting for the next episode to come along. No, we'll have a period of focus. So we are going to go into a little fallow period now. But I don't know. I think there's a plan here. I think we've scratched the surface of this one. I think we've covered loads of exo things over the last 6 episodes, but I think we've only just scratched the surface of this thing called life.
I think you're right. And every time I sort of tried to narrow this episode down, I could just feel the whole topics just falling away to each side and thinking, oh, we should pick that up as a whole episode. We should pick that up as a whole episode.
Because, I mean, surely this has got to be one of the big areas of astronomy for the future, for the foreseeable future. You know, so much has happened in the last couple of hundred years, but particularly the last couple of decades. An exponential increase in our ability to find exoplanets, to understand, neutron star mergers and all sorts of amazing things. We can do so much now. But this question of, are we alone is so fundamental. It's so big. And
we've touched on it loads of times throughout our back catalogue, if you like. But that we've by no means even touched on all the, I guess, interesting points that have been around for the lifetime of the podcast.
Yeah.
But even pushing that aside, this is a topic that just moves on every week. I mean, it's hard to keep up with. And so it's always worth coming back and saying, what's the 2025 view on this? Because that could be very well different from the 2024 and previous.
Yeah. So I think what we're saying, listener, is season 3 coming your way down the track, we'll give you a heads up, is going to be about life.
Yeah.
Life in the universe. We'll tear that one apart over 6 episodes. What do you reckon, Emily? Shall we get together and discuss a plan for that in April? I'm off to Australia for a month. So when I get back, we'll put a plan together and aim for, what do you think?
Yeah.
May?
Yeah, April, May sounds great.
Yeah. So we're going to take a little bit of a break. It's been fun. We've had a great time on this episode. Take a bit of a break and we'll see you for season 3 in May. But in the meantime, if people wanted to get in touch and congratulate us on the amazing job that we've done with season 2 and throw us ideas for season 3 and beyond, they can get in touch with us. How?
Well, we've still got the interwebs going.
We have, thank goodness for that.
We've got a website, Syzygy.
Thank goodness for the interwebs.
.fm, syzygy.fm, and that is there's a contact page on there. You push a button, you type your thing in, and it comes to us whooshing through those magical tubes.
It really, really does. And that's the best way to get us. We are out there in various ways on various kinds of social media. But look, I think we can all agree in 2025, social media is a challenging place to be. So let's just say, just go to syzygy.fm and find us there.
It's very safe there.
It is. It's a wholesome place to be. No one's going to abuse you on our website. Instead, you can find all the past episodes with all of the beautiful show art and everything that's on there. You can find the list of all of our fabulous supporters. And if you wanted to become a supporter, then you can do that by going over to patreon.com/syzygypod and throwing a couple of dollars or pounds or whatever your local currency is, our way every month to help us keep the electrons flowing through the website and to do the things that we do. But otherwise, just tell everyone you know that there's this great thing called Syzygy, and they should listen to it because it's awesome. We're going to see you for season 3 in a couple of months' time. Emily, it's been really nice. Great to see you again.
Let's do it.
All right, everybody. Catch you soon.
Bye.